we're going to look at an important vector space, if you will, or subspace, and it deals with linear combinations of vectors. And we've looked at linear combinations of ordered n-tuples and matrices, and so this is a natural extension of something we've already been talking about. Focus that in a little better. Okay, if we have U is a vector in some vector space V, and this is the way we'll write that. The little symbol there, if you don't remember, means is a member of or is an element of. So the vector U is in, we say, the vector V, or is an element of the vector space V. If that's the case, then U is said to be a linear combination of the vectors. Now look at these vectors, V1, V2, and so on. These are vectors. These are subscripts on these vectors, so be careful. We use subscripts on components in vectors. Those are real numbers, but notice the arrows. It's going to be real important that you use arrows over vectors, and you see these scalars K here. They don't have arrows over them. So we have R vectors that are in the vector space V. So U is said to be a linear combination of these R vectors if we can write U this way. This is a linear combination. That's what we call a linear combination. And these scalar quantities in front of each vector, K1, K2, and so on, these are called the coefficients of the linear combination. Okay. So here's a theorem that we're going to prove. If S is a set of R vectors from a vector space V, then the set W of all possible linear combinations of S, linear combinations of the vectors in S, is a subspace of V. So in other words, if I take any possible linear combination of these vectors V, I will get a vector. That vector is going to be in this set W. And this set W, we're going to say, is a subspace. So how do we prove something's a subspace? We've been talking about it. Two things we need to prove, right? It's a subspace of what? It's closed under addition and closed under scalar multiplication. Clearly these vectors, right, are in a vector space, right? And so any vector in W is a vector in the vector space V. So it is a subset, but we have to prove it's closed under addition and scalar multiplication. So I'm going to let, and again, arbitrary, I have to do this in an arbitrary way. Let U and W, we'll say, be in this set W of all possible linear combinations. Okay. Well, thus, what do we know? Well, U has to be a linear combination of these vectors, and so I'll write it as the following. I'll use A scalars, A sub 1 times V1. Notice this is the scalar, this is the vector, plus A sub 2, V sub 2, all the way to A sub R, V sub R, right? So if U is in the set W, it's a linear combination of those vectors, and there must be a way to write that, where the coefficients for U are A1, A2, and so on. And I also know the same thing for W. But W doesn't have to be the same coefficients, right? So I'm going to, arbitrarily could be different. I'll say B1, B1 plus B2, B2, and so on. All right, so we know those two facts. Okay, this is kind of the, remember I was saying the things we know. This is what we know, and now from what we know, we're going to show that we're closed under addition and scalar multiplication. So let's look at U plus W. Now, if I add these two vectors together, I can combine, right? And since the coefficients of the vector V1, right, now becomes what? A1 plus B1 times V1 plus A2 plus B2 times V2. And here, really we're making use of the vector space axioms that we can use, because again, these vectors are in W, they're also in the vector space V. And then the last is what? AR plus BR times VR. So, is this vector in the set W, right? We started with vectors in W, we added them together. The question is, are these in W? Is it closed? Is W closed under addition? Well, what do you have here? What do you have here? What is this? A1 and B1, A2, B2, AR, all those are scalars. When I add two scalars together, what do I get? What do I get when I add two scalars? I get a scalar. This is a scalar. This is a scalar multiple of V1. It's the coefficient of V1. This is the coefficient of V2. This is the coefficient of VR, and so on. This is a linear combination, right? Linear combination of the vectors in the set S. In the set S, there's a linear combination of those vectors. Well, if you're a linear combination of the vectors in S, W is the set of all possible linear combinations of the vectors in S. This must be in W, right? So this is the support. What about scalar multiplication, right? If I look at for any scalar k, if I multiply, say, either vector u, what happens? Multiply every one of, distribute the k through. I get k a1 v1 plus k a2 v2 all the way down to k ar vr. So is this vector in the set W? Well, again, I'll have you note that k is a scalar, a1 is a scalar. Multiplying two scalars together, what does that give me? A scalar. This is a scalar, this is a scalar, this is a scalar. This is a linear combination, again, of vectors of S. And so this also is in W. We're closed under addition, we're closed under scalar multiplication. That's the proof. That's all it is. So this set W of all possible linear combinations, in other words, if I grab any arbitrary vectors in the set, in the vector space V, rather, if I grab any arbitrary vectors from the set V, form a set of them, and the set of all possible linear combinations of those vectors, they form a subspace of V, and they are, and they form a subspace, is what we've proved. So let's give this new subspace a name, basically. So here's the definition for any set of vectors from a vector space V. The subspace W consisting of all possible linear combinations of vectors in S is called, well, subspace of V generated by S. That's pretty lengthy. Or the span of S. And that's what we'll just say, the span. So we say the vectors V1 through VR span the set W. And we can write this way. W is the span, and then in set notation we list the vectors, or W is the span of S. You'll see where S is already stated to be that set. Now, what is a spanning set? What are some common spanning sets? Well, there's many, but here are some that we're familiar with. Do you remember these guys? In fact, I've used the notation you're familiar with, I, J, and K, these vectors in 3 space. They form a spanning set for all of 3 space. They span all of 3 space. Right? Every vector in 3 space can be written as a linear combination of these 3 vectors. So does that make sense? I mean, that when we talk about this, that's a little abstract, but this is an example, right? 3 space is a vector space, and these 3 vectors do span it. Now, it's not the only spanning set, as we'll see, but it is a very common one, and one that we're familiar with. These n vectors here span all of n space. Okay. What's the spanning set for P sub n, the set of all polynomials of degree n or less? So a polynomial of degree n or less is, going to be something like what? It's going to have, a x to the n plus b x to the n minus 1 plus ... I probably shouldn't use that. Let's use a sub n minus 1, and then we'll have a1x plus a0, right? But all these coefficients here, it's a, right, are real numbers, but the vectors are, right, x to the n minus 1, and so on. So those are the vectors, right? Any linear combination of these guys, they span P sub n, the set of all polynomials of degree n or less. Notice there's a total of n plus 1 vectors here, right? Because we have x squared all the way x to the n, so there's n of those plus the 1. So that's like, all your x to the n minus 1, and including your constant terms. Okay, so these are some common spanning sets. Let's find some other spanning sets for some other situations. Let's find a spanning set for M22. How might we do that? Well, let's just think about what is M22. M22 is the vector space consisting of the set of all 2 by 2 matrices. So an arbitrary 2 by 2 matrix will look like what? Each entry is arbitrary, so they don't have to be equal. They can, but I'm going to make it most general, right? So each of these could be different values, A, B, C, and D. So that would be an arbitrary matrix. So what would be a spanning set? What would be a set of matrices, in this case, obviously 2 by 2, where any such linear combination, I can express this matrix as a linear combination of those matrices. And I'm going to give you some help here. Okay. Now this is not the only spanning set for M22, but it will be the obvious one. I want you to fill in the matrices with the right numbers to make this equation true. Can you do that? I hope so. Here's what it should be. All right. This is a linear combination of 4 matrices. Every 2 by 2 matrix can be written as a linear combination of these 4 matrices. So a spanning set for M22, what is a spanning set? A spanning set is, or can be, these 4 matrices. It's not the only spanning set for M22, but it is one that's sort of obvious. Let's find we'll do one last one and then we'll go on to another video. Let's find a spanning set for 3 by 3 upper triangular matrices, which actually forms a subspace of M33. And the reason it's a subspace of M33 is that if you add any 2 upper triangular matrices together, you get an upper triangular matrix, closed under addition. Scalar multiply any upper triangular matrix, you get an upper triangular matrix, closed under scalar multiplication. Okay, so what would a 3 by 3 upper triangular matrix look like? Well, remember, upper triangular means the main diagonal entries below the main diagonal are 0. Remember, for upper triangular, entries below the main diagonal are 0. So we've got zeros down here, but the entries along the main diagonal and up above can be arbitrary. So I'm just going to put arbitrary letters for each entry, because these entries, they could be anything. They can all be different. They can all be the same. You know these 3 have to be 0, though. Okay. So I could come back, I could do something like this, like I did here a minute ago, right? Think about it. Of course, it's going to be a linear combination of 3 by 3 matrices, right? So I'm going to have A times a 3 by 3 matrix plus B times a 3 by 3 matrix plus C times a 3 by 3 matrix, and so on. Do you see what those matrices will be? So what are they going to be? A spanning set for the set of 3 by 3 upper triangular matrices is going to be this. A times what? This matrix plus B times this matrix plus C times this matrix plus D's right there in the middle, right? So I'm going to put a 1 right there in the middle. And so on. Here's the one for E. And here's the one for F. Okay. Whoops. Okay. So there's the set. A set. It's not the only one. Now, some of the questions we're going to look at later on are, you know, in this spanning set I see there's 1, 2, 3, 4, 5, 6 matrices. Okay. There are other spanning sets. Does every spanning set have to consist of 6 matrices? Can we have a spanning set that consists of fewer matrices? Can we have a spanning set that consists of more matrices? If you think about it hard enough, you'll say yes. But we'll investigate this behavior a little bit later in Chapter 4. Okay, so that's the idea of spanning sets. In the next video, we are going to take a look at how do we determine whether a set of vectors spans a subspace. And then we're going to look at a particular subspace of interest to us known as the solution space to a homogeneous system of linear equations. So we'll do that in the next video.